Today on Xenodiladon, I'll be using words such as crystal, energy, vibrations, frequencies, and wavelengths. But don't worry, this isn't spirit science and I haven't lost my mind. In this video, I'll be talking about Polychromatic Acousto-Optic Modulators, or PCAOM for short. Before I show you what a PCAOM is, there are two things I want to show you. The first one is a dichroic filter, dichroic mirror, which is a good example of a Bragg mirror, Bragg reflector. And the way these optics work is they use a coating with various density or thicknesses or different properties, which allow light to either pass or reflect based on the constructive interference that is generated by the coatings. So, for example, this is a reflect blue and pass red. Let's take a look at that. So it reflects blue. Let's take a look at a red. And it mostly passes through that. So that's one property to keep in mind, is that we can control the general wavelength or group of wavelengths that goes through a material by changing the spacing of a surface or the coating. The second property is diffraction. For that, I'm going to show you the red laser once again with a diffraction grating. Let's take a look at that. So there's our laser dot, and we'll put the grating in front of it. So this is a 2-axis diffraction grating. Here we have the Y and the X. And we can see that we have a bright dot in the middle. That's going to be our 0 order. And if we think about this, this is going to be our -1 and our +1. So we call that the first order and minus first order. And that would be on the Y. We got the first order and minus first order. Though in general, this would be first order, and we go out second order, so on. And it really doesn't matter, but that's how orders are explained. So this is a good demonstration of how surface geometry can diffract. So there we split up the beams. The device that we're going to be taking a look at in this video not only selects color, but it also changes the refraction of the material. And it does that through the use of ultrasonic sound. I'm going to set up a helium neon laser and we'll take a look at the PCAOM. Before I continue with the demonstrations, let's take the cover off the PCAOM and see what's on the inside. I haven't opened this up before, as it's not mine, and I would like to thank my friend Adam for letting me borrow this with the hopes that I won't break it. There is a video of this device on his channel, and I'll link that below in the description, as well as a couple of other videos and papers that you can read, so that way you can learn more about how these acousto-optic modulators work. Alright, let's see what we have on the inside. Let's see. Given the way it's cut, this probably works in the Bragg regime and not in the Raman Nash regime. So that would give us the 0 order and a first order, but no more than that, where it uses waves that aren't standing. So it probably only has one transducer, whereas the other ones can have a transducer on each side. Let's see what we have. If we can find the transducer. Oh, I see some gold wires right here. So up on the top in this section, there's some gold wires. So this side is probably the transducer side. The whole crystal could actually be a transducer if it's quartz or another material that has a piezoelectric effect. On the bottom side, it's either going to be the other side of the connection, or it's going to be the acoustic absorber material. And what that does is it prevents the crystal from being directly on top of the harder material, so it prevents cracks, and it also prevents waves from being sent back into the crystal, reflecting off the surface, and causing different waves in the crystal that are undesirable. So, I'm not sure what that crystal is made out of, but given the cut, it definitely looks like it's based on the Bragg diffraction. So, the way this works is instead of using different layers of metal oxide like a dichroic mirror does, Bragg reflector does, this uses sound waves to cause different compression waves in the material. So the amplifier sends in a sinusoidal signal, not a sinusoidal wave, which causes the crystal to send compression waves through the material, or the PZT, piezoelectric transducer. So there will be sound waves that travel through the crystal. Now, unlike other ultrasonic devices that usually operate in the kilohertz range, these can operate well into the megahertz range. So this one could operate in the dozens of megahertz to the hundreds of megahertz, and some faster ones operate into the gigahertz range from what I've read. But anyway, so instead of using metal oxides to diffract the beam, what ends up happening is when the material is compressed and it's rarefracted, it's made less compressed. What this does is it changes the elasticity of the electrons in the crystal. So some electrons are able to vibrate a little bit more. Some electrons are kind of in a tighter state of vibration, kind of like you're stretching rubber bands. They get tighter to stretch. And it's the difference between the compressed and the rarefied portions of the crystal that gives us our diffraction. So you were to think about it like this, it kind of operates like a dichroic mirror, but it also operates like a diffraction grating. Instead of having surface geometry, we can see it on the front. Let's see, a little bit of a holographic effect there. Instead of having different lines in the material, we were to think about it like this. The lines carry through the crystal entirely. So you got full waves in the crystal, and those are what gives us our diffractive properties. Pretty interesting setup. It looks like we have a few LC networks on the top, probably for tuning. I see 2 capacitors, 3 little inductors. It's all very high speed stuff in there. And either 2 tunable capacitors or resistors. Probably capacitors, given that it looks like it's an LC network. Probably for fine-tuning the crystal. Pretty interesting. I'm going to put the cover back on this, and we'll send the helium neon laser through it. Later on, we'll take a look and see if we can see any changes in how the crystal looks as it's operating with the cover off. So put the cover back on, and we'll get this set up. Alright, let's go over everything I have set up here on my desk. I have my adjustable power supply here, which is providing me 15 volts, which will be driving this little helium neon laser power supply, which of course drives this little helium neon laser tube. It's a randomly polarized 1 milliwatt laser. That'll be important later on in the video. I have this little 12 volt power supply here, which is running this fan and this fan. Of course, this one keeps this power supply cool, and this one keeps the Acousto-Optic Modulator driver cool. The reason why these generate a lot of heat is because you're sending out a sinusoidal wave. So the transistors in here, they're not always fully on. So they're more resistive than, say, a MOSFET, which has a low on resistance and therefore doesn't generate a lot of heat. In this case, because they're operating in the linear range, linear fashion, they're going to generate quite a bit of heat because of that. I have this 24 volt power supply here, which will be powering the Acousto-Optic Modulator. Now, something to note, this is RF, and RF is a little weird. When you're dealing with RF amplifiers and stuff like that, it's always important that you have them properly loaded, otherwise they could damage the equipment. You'll see this with like radio transmitters and other RF stuff, but it really does need to be loaded. It's very important that you do not connect one of these up without having it connected to a modulator or another proper load. Alright, so what I'm going to do is I'm going to plug this in. And now to run this, as far as the signal, you have two options. You have the TTL and you have the analog. This is familiar to those of you who have watched my channel. You're going to understand these because I deal with those terms working with show lasers quite a bit. I'll be using the analog modulation in. Unlike the show lasers that use 5 volts for the analog modulation, these operate on 10. This particular brand, I'm not sure if other brands do, but to do the modulation input signal, I have here 2 rechargeable phone batteries, lithium-ion cells, which will give me 8.4 volts together. I have a little 50K potentiometer acting as a voltage divider with this sweeper connected between 2 outer pins. One of them is ground, one of them is positive, 8.4 volts, and that'll let me select a voltage range between 0 and 8.4. Now I have the positive output, or the sweeper, connected to the red wire here, which is the modulation pin for the analog, and I have this set to the helium neon laser frequency of 632. So I'll go ahead and connect this up as well. Alright, and the last thing I'm going to do is connect up the helium neon laser. I don't want to run it longer than I have to, it is quite pretty. Now let's go ahead and see what our output is, now that we have a good idea of everything going on the desk. Alright, now alright, I'm going to turn on the helium neon laser. We should see a nice red dot as a result. Just like that. You really can't see that. I'm going to turn off the shop light. There. That's how you do lasers. Alright, so now the wire is inconveniently in the way, but that's science for you. Nothing is easy. Go tilt that a little bit. Alright, so we have the laser. It's not going through the crystal right now. You can see that the beam is right over here where my finger is. And when I put the beam through the crystal, you'll see that the beam drops down a little bit. So go ahead and move this over, and then we can go ahead and get everything all set up. Let's see, that's through the crystal, and that's not. So oh, it goes up. Okay, I was wrong. It moves the beam upwards, but you can see it. So through the crystal, not through the crystal, through the crystal. And now that we have it set up through the crystal and we have it running, then we got to find the angle of which is optimal for splitting it. Now remember, earlier in the video, I mentioned that it was an unpolarized or randomly polarized helium neon laser. Now, because of that, we'll only get a 50% efficiency on this. So the best we can do is to take this output and make 2 beams 50% the energy. If it was a polarized laser, we would get a higher level of efficiency, and a good one can reach up to 90% efficient, so we'd get 90% of the beam shifted. Well, let's see if I can find the angle. Let's put in a little bit of a signal. Well, that's actually really well lined up right now. Awesome. Alright, so I'm going to try to zoom in. Alright, so you see that. You can see that. Excellent. Alright, so as I turn up the voltage for the modulation for the red, I have moved it ever so slightly. Please send your spare optical table to my address. There we go. Alright, so don't you move. Alright, I'm going to turn it down. Turn it up. And you moved. Alright, I'm going to get a better angle at this so you can take a look at this better and carry on with the demonstration. One of the trickiest things to understand about PCAOMs is that even though the sound waves change to the refractive index of the material, it actually generates a diffractive effect. So I'm going to show you that we get a distinct separation right there, and you'll notice that the dot appears on the bottom. We can think about the original dot is our zero order, and the lower dot as the negative first order. So if we change the angle of the acoustic modulator, we can actually get the dot to appear above it within a like angle. Let me go ahead and do that. Alright, so now we have a first order dot, just like you see on the diffraction grating. And I think we can get both those just a little bit at the same time. Yep, just a little bit. Now that I've gone over what's inside an acousto-optic modulator and how it works and diffracts light, I want to talk a little bit more about thin film optics. So here I have a microscope slide, and I have a microfiber cloth that has some rubbing alcohol on it, and I'm going to wipe the surface, and as the surface dries, you'll see that there is some color that comes off. That's thin film interference. So what happens is when you have a really thin layer of materials with different refractive indexes, it'll cause constructive interference and destructive interference, and depending on the thickness of those layers, you'll get different colors. And the reason why we get different colors here as this dries is because the layer of alcohol is getting thinner and thinner and thinner, and interacting with different portions of the light as far as the wavelengths. To show you this effect a little bit more, I have a polarizing filter that's pulled from a video projector, and on one side we have the polarizing filter itself, the polyvinyl alcohol, and on the other side it's just glass with an anti-reflective coating. But since these are already coated, we'll get a much greater effect by interacting with the surface and then the coating that's on there, and get much brighter colors. So I'm showing you this because it's very important to understand that the change of spacing between the different layers has an effect on the color. You'll see as it dries, the colors shift, just like that. Now, why does this look familiar? Well, you'll see this a lot in things like soap bubbles and oil spills, but it's also the same thing that's happening with things like Bragg reflectors and dichroic glass. So there's no dyes or pigments in these, but it's a thin film coating on the top, and depending on the spacing of those coatings and the refractive index of the metal oxides that make those coatings, we can get different properties, how it interacts with light. Alright, now that you understand a little bit about how wavelengths can interact with different spacings of materials and layers, let's talk about the polychromatic aspects of the acousto-optic modulator. As the name suggests, poly meaning many and chromatic meaning color, this not only modulates red light, but can also modulate a few different other frequencies. Those frequencies being 514, 476, and 488. Some of you will recognize those wavelengths as ones that come from an argon ion laser, which I have right here. Now this laser is a multi-line, unpolarized argon ion laser, and it puts out 6 lines. These lines range from the green into the blue. Now, the original intent of this laser unit was to cure UV curable resins. So the green lines are a bit subdued, they're not as bright, but we'll get some strong blue lines. So I'm going to turn this on. We're going to hear an adorable laser startup noise. And we'll take a look at the 6 lines that come out of this laser unit. It does take a little bit of time to warm up though. To demonstrate the lines, I'll be placing this diffraction grating in front of the laser beam once it's fired up. And we can take a look at the 6 colors that make up the beam. Oh. Alright, here we go. Turn off the light. Turn on the laser. There we go. Let's see, make that. Alright, now put the diffraction grating in front of the laser beam. And we'll see that it splits up into different colors. I'll move the camera over. Take a look at those. So those are the 6 colors that are coming out of this argon ion laser. Right, now it's time to see exactly what polychromatic actually does. So here I have a couple of momentary push button switches, one for each one of the output colors from the PCAOM controller. So I have my 0 to 8.4 volt reference coming from this wire. That's coming from the 2 lithium ion cells and the potentiometer. Going to that white wire, and that white wire is connected to each one of these switches, and then I have an output wire that goes to the analog modulation for each one of these selectable colors. Right now I'll be using the ones that are able to be tuned in the argon ion, so the 514, 476, and 488. Now mind you, the green's not going to be that bright because the greens are suppressed. We're going to get a lot of blue, well, the lines that are strong that are blue. Not an ideal setup. It's a randomly polarized light, so that means that we're going to get 50% efficiency per color, not per the entire beam. So I'm going to get a focus on that. Going to turn off the shop lights, and we can see exactly what that looks like. Alright, now, can't really run the argon ion too long without blowing circuit breakers, so here we go. Alright, I want to give you a really good idea of what's going on. Zoom in. Alright, so now if I press one of these buttons, you can see another dot appear. So that's the green. Bring that down. Green. That would be, I think, the 488. And then a deeper blue line. So I'm able to select which color I want. Pull a little bit of fog in there, see how it looks. Move this over. It's not really impressive when you're only dealing with a couple of milliwatts at best. But we're able to adjust what color goes through by changing the frequency, the sound that goes into the crystal. And just like how we get a change of color reflection by altering the thickness or the changes of space between the layers on a thin film optic, we can select which color we want to be diffracted out of the Acousto-Optic Modulator by changing the frequency, and then the amplitude changes how much gets passed through. Let's set up the helium neon laser and run all 4 colors and see how impressive we can get a 2 milliwatt mixed gas beam on camera. Before I get into the next and more or less final demonstrations, I'm going to go over just how far away from the ideal setup I really am. It's comical. So the first problem is the argon ion laser is not only randomly polarized but has suppressed green lines, which means that even though we do get some green out of this, it's really weak and it's randomly polarized, which means that we only get 50% maximum efficiency out of the Polychromatic Acousto-Optic Modulator. That's problem number one. Problem number two is the randomly polarized helium neon laser has 1 milliwatts, which means that maximum modulation out of the modulator is about half a milliwatt at best, which isn't a lot of light, especially when it's red. Problem number two, not a proper optical setup, which has its own problems. First of all, I got a first surface mirror right here, which bounces the light from the argon ion laser over this dichroic mirror filter right here, and mixes the helium neon laser and argon ion laser light into more or less one beam. Now, a polychromatic acousto-optic modulator is very sensitive to the angle of incidence that the beam is going into the crystal and through the crystal. There is a slight misalignment in the near field array that I have here. They're not quite aligned, and that means that the angle of incidence going into the crystal is slightly different. So, even though I have it optimized for the helium neon laser, because that's my weakest color, it is not optimized for the correct angle of the light that is coming out of the argon ion laser, thus making it even less efficient. But it gets better. Remember when I said that the acousto-optic modulator can take a modulation signal of 10 volts? Well, I also said that we're using 8.4 volts tops for the modulation input. So that means out of everything that I have here, the light that I'm getting off the lasers, 50% modulation, plus losses, plus incorrect angle, plus only 85% modulation voltage going into the analog inputs, means that I have a whole bunch of losses in this entire setup. A bunch. And we're only going to get maybe a full milliwatt after everything is all done and settled. I'm going to turn off the light and we can see what the optical train looks like, and then a little bit of what this looks like over here. What rubbish video footage that was. So, I've changed the setup slightly in a vain attempt to get better. Here's what I've done. I've taken and changed the helium neon laser position to shoot this way towards the camera, and out that way. Once again, it's going through the dichroic mirror and filter, and then out of the acousto-optic modulator. Instead of having the argon ion laser bounce off of first surface mirror first, and then to the dichroic filter, it's now coming directly out, and then reflecting off at roughly a 90-degree angle off the dichroic filter there. So that goes out through the crystal. Now that's my new setup. Hopefully this will look a lot better. that video footage looked a lot better. Now, as I was doing that, I did come up with some other tests that I could do, and it might answer some of your questions, might answer some of mine. I definitely have some, since this is the first acousto-optic modulator that I've played with. And play with it we shall. Now, one of the questions that came to my mind is, will we get better efficiency if we linearly polarize the light coming off of a laser? We should, right? Alright, so here's what I'm going to do. I have a piece of linear polarizing film here, nothing special, and I have a little arrow on the top to indicate which way the E field is going. So, in a gas laser, ones that are polarized has something called a Brewster window in it. And a Brewster window is a piece of glass that lays in the resonator between the output coupler and the high reflector, and it polarizes the light. You can look up on Google what that does, or if you want to learn a little bit more of that, go and watch my argon ion laser introduction. You'll see what a Brewster window looks like on a laser tube. But anyway, will we get better efficiency if we use a polarizing film? Let's see. So, the Brewster window is normally this way in a gas laser, so the E field is usually up and down. So we'll put it in this way, turn off the shop light, and let's modulate. So that's what we get before, and we'll put this in. Oh, that's dirty. It's about the same. Well, what happens if we put it horizontal? Yeah, that cancels out. A piece of polarizing film really should be cleaner than that. What a rubbish optic. Let's put it in front. Let's see. First, we'll do it with the polarizer in the vertical. And I don't really get much out of it that way. Let's try it in the horizontal. That's interesting. Seems that the light that is being diffracted, the first order output, is polarized horizontally. So it seems like the acousto-optic modulator not only diverts the light coming out, but it also flips the polarization by 90 degrees. I was expecting a little bit more of an impact as far as efficiency, with maybe putting that polarizing filter in front of the helium neon laser, but it's not exactly a laboratory grade polarizing film. I cleaned it off a little bit. See what we get. Is that better? A little bit better. Yeah. And you probably wouldn't get any efficiency like this anyway, because I think you lose about 50% of the light when you use a polarizing film. So max efficiency is going to be 50% either way you look at it. So this isn't going to be a cheat if you're using an acousto-optic modulator. Either way, you're using losing 50%. But that is interesting. So the original beam that's coming out maintains its original polarization, but the diffracted beam, the diffracted beam definitely in the horizontal. That's interesting. Yeah. So here's another thing I want to do. Let's take a look at the controller. Now we have this section here. That's for the red output. We have the 632 nanometer selection on because we're using a helium neon laser. But we also have another color here, the 647 nanometers. It's usually a line that comes out of a krypton laser or an argon krypton mixed gas ion laser. But I do have a couple of diode lasers in that range. I have a 650, a 660, and I also want to test a 473 nanometer DPSS laser in this, see what efficiency we can get out of that split. The 473 nanometers is going to closely line up with the 476 here, and yeah, it'll be interesting to see if the 660 works. At this point, I have the Acousto-Optic Modulator set to the 647 nanometer setting for the red. And the first laser diode that I want to test out is this one right here. Not exactly sure what the frequency is, but I'm pretty sure it's 650 nanometers just by looking at it. It's a pretty mid-range red. To test that out, I have it going through the Acousto-Optic Modulator, and I have my output right there. And I have the modulation voltage going into the controller set at 8 volts. So I have a linearly polarized laser light source, and we should get above 50% as far as the efficiency. I've gone too far. That's the one I want. Alright, let's see what we get. Looks about 50%. How can we get better? Bring up the modulation voltage to 9 volts. It's still about 50%. I go and adjust the angle real quick. See if we get better. Well, yeah, that isn't much better, surprisingly. Let's go ahead and see if we get the same effect with this. So let's put the polarizing film with the E field in the vertical. Yeah, and it blocks out the output. And if we put it in the horizontal, we should block the original beam. Yeah, we do for the most part. Oh yeah, we get a much brighter output, since the output that's deflected from the Acousto-Optic Modulator is in the horizontal polarization. Yeah, that's interesting. That's cool. Actually, I want to see exactly how well that laser diode is actually polarized. Yeah, that's pretty polarized. Alright, the next laser I want to try is a 500 milliwatt 650 nanometer laser. Zoom out. We'll go ahead and plug that one in. Set that one up. Be gone with you. Plug it in. Alright, that's going to need to be raised up just a little bit, looks like. Let's see what we have for quick shim. That'll do. Oh, the fan's going to make that go under. Stay. So it's a pretty wide beam. So we're going to get some cast off, but that's pretty good. That's our output. Let's make sure it's in the correct polarization. So I'm going to test that real quick with the polarizing film and hopefully not burn out another hole in it. Yep, that looks incorrect. Alright, so I gotta rotate that 90 degrees. Alright, that looks pretty good. Don't move. Alright, once again, we're going to get some cast off because it's a pretty wide beam, but that should be in the correct polarization, which it is. Alright, let's see how well aligned that is. And we're going to need to move the crystal a little bit. Alright. Yeah, we're going at the speed of real science now. Alright. So, that's our output. And, And once again, we get about, and we get less than 50%. Wow, that's really bright. You can't see squat, can you? There we go. Yeah, that's less than 50%. Wow, I'd expect to get a lot more. It does seem like the lower dot is slightly darker, so it could be that this is a really broad band multi-mode laser diode too. Not exactly sure what the spectra looks like on there, but its center wavelength should be about 650 nanometers. Huh. It doesn't seem like the diode lasers really give us that 90% efficiency we're looking for. Interesting. Alright, one more red laser diode to test. That is going to be a 660 nanometer DVD burner laser diode. I'll unplug that. Let's see if it'll do 660. That's over 10 nanometers out of its listed range. So if it can do 660, it'll be able to do 473 nanometers, no problem. Alright, let's check the polarization on that. Make sure it's in the vertical. Nope. Flip this 90 degrees. Alright, now we're good. I'll put that through the modulator. It's going to need to be raised up a little bit. Yeah. Perfect. All right. Let's go ahead and see how well that wavelength works. And modulating. Well, that works right away. You can see it there, right on the top. See if I can get a better angle on that. So, oh, that's really well. That's working really nice right there. Probably the best result I've gotten so far. It really likes the 660. Of course, because it's a DVD burning laser diode, it has really nice beam characteristics. But wow, that's over 50% for sure. It looks like. Should get the laser power meter out and measure that. All right, let's try to test the efficiency that we're getting. So to do that, let's take a measurement of our full output power. See what that is. Reach. About 200 milliwatts. So all we need to do is get more than 100 milliwatts down. Let's get a good angle on that, and see what we get. All right, do some fine tuning. It really is a touchy angle. All right, I think that's the best we're gonna get. Let's carefully. All right. About 150. 140. Yeah. So let's say about 75% efficient, which isn't too bad. Finally, I have one of the 473 nanometer DPSS lasers. These things are by nature horizontally polarized, so it's in the correct orientation. And let's go ahead and take a look at the output efficiency. Now, this is a very polarized laser, so we can go ahead and almost completely block it with the polarizing film. And go ahead and press a button, see what we get. Shot blade off. Alright. Yeah, I'd say maybe that's 30-40% efficient. See if we can get a better angle on that. Still about 40% efficient. Let's try get a top reflection. Maybe that'll work better. Top diffraction. Yeah, we're not getting that either. Usually I can get a dot on the top. It does not like the 473. Yeah, about 40% at most. Let's once again take a look at the change in polarization. So here I have the polarizing film in front of the output in the vertical sense, and we can see that the diffracted light is not passed. If I go and flip this into the horizontal, the laser light is almost completely blocked out, but we do get the output because the outputs change. It's rotated by 90 degrees and is horizontal. So, yeah, just by rotating that, output in the horizontal and the original in the vertical polarization. Let's go ahead and take the cover off this Acousto-Optic Modulator driver, see what's inside, because if I don't, somebody will complain about it. Once again, I'd like to thank my friend Adam, who let me borrow this to make a video on it, in the hopes that I'm not going to break it. Actually, Adam is a really good friend of mine. He's a fellow laserist who lives in the same state as I do, and we often hang out, do things with lasers. He helped me with the argon ion laser video that I posted up. But not only that, he's taught me a lot about high vac stuff, test equipment, power supplies, all sorts of industrial gear. As one of the things that I do is help him fix stuff for his eBay store. I'll link that below in the description as well. It'll be the last link. But one of the things that you can do to support this channel is purchase stuff from there. Because the more you buy, the more we buy. And maybe we'll get more stuff on the channel that way. It keeps the sponsors away. Alright, well, let's see what's inside. What wizardry lies in the box. It's all going to be analog stuff, and you're going to have mysterious RF things inside. Stuff I'm positive Adam is going to know more about it than I am, but let's see what we have. Alright. Let's get closer to it. Looks like we have this chip right here. Could be a quad operational amplifier because it takes an analog signal in. And this right here could be some kind of voltage regulator. But from here, it's all going to be pretty much RF magic. See if we can make some sense out of it. I see 4 little crystals here. So these, what they do is they generate a signal. Probably going to be in the RF range. Let's see if we can see what they say, because that's going to be the frequency that's going to go out to the amplifier. I can't really read that. What I'll do is I'll mark them in captions right now. There you go. Moving on. From there, the signal's generated in these, and it goes to That's these. I don't know what those are. It could be opto-isolators or optocouplers. Seems to be two of them. And then up here we have a very special transistor. So you have 4 leaded component right there. Those are really fast transistors that work in the RF range. So usually in the megahertz or gigahertz range. They're really weird looking components, but you don't see them very often in normal stuff. Looks like we may have a little filter here. That'll be we're getting rid of some noise, or it could be for harmonics, but given that these all look the same, I think they're for filtering. We have these right here. It looks like these are either tunable capacitors or resistors. I'm betting they adjust the gain, so they're probably going to be variable potentiometers or resistors. And it looks like from there, they all join in the center here. So I'm going to guess that this is where all the RF signals join together. Remember, we can use more than one color, so all the individual signals are generated by each one of these crystals. Oh, there's 2 of them. The red channels have their own crystal. That's nice. This must select between the 2 of them. Well, it does, but between the 2 crystals. So one of them is going to be for the 638, one of them is going to be for the 674. Interesting. Yeah, so all the outputs from these transistors look to be fed to this point, and the gain or the output probably going to be adjusted by these. I think they're variable potentiometers. Once they connect here, it looks like it goes probably to the underside of the board and over to here. I'm going to guess that this is the main output amplifier, so whatever signals are joined together at this point, probably going to be a trace under the board, which is going to go out to this component. And then it's also going to have the RF output on here. I'll see if I can find a data sheet for this and link that in the description as well. It's probably going to be a really interesting RF output transistor. I think that's about, what, 8 watts? That's a good guess. I think this does 8 watts. Kind of astonishing how warm that gets, actually. So the whole bottom plate does get rather warm when this is running. Once again, it's because it's running in the linear range and it's outputting a sinusoidal signal. Somebody needs a muffler. It's outputting a sinusoidal signal, so it's going positive and negative, I think. And that's what makes the compression waves in the crystal. Piezoelectric transducer. Yeah, really cool stuff. Well, that's really it for this video. Not much more to go over. Coming up in later videos, not only will I be doing more with gas lasers, such as the ones you saw in this video, but I also have a bunch of GPSS lasers that I'm excited to get to as well, such as these 488 nanometer lasers that are manufactured by Melis Grill, and a couple of interesting yellow lasers that use self-doubling laser crystal technology, including this 560, 565, and some 575 nanometer lasers. So you know what to do. As always, stay tuned for more.